मेकॅनिझम ऑफ रेस्पिरेशन सुरू केलेला आहे आणि त्याच्यामधला पहिला 2 पॉईंट्स ए आणि बी म्हणजे ब्रिदिंग आणि एक्सटर्नल रेस्पिरेशन पूर्ण केलं. आता आपल्याला तिसऱ्या पॉईंटकडे म्हणजे सी इंटरनल रेस्पिरेशन शिकायचं आहे. तत्पूर्वी जे 2 पॉईंट झाले त्याच्या नोट्स मी तुम्हाला पाठवलेले आहेत आणि त्या नोट्सचा वापर करून तुम्ही स्टडी करायचा आहे. काही शंका असतील तर मला विचारायचे आहे. बरोबर. सो नाउ टुडे we'll start with the third point of internal respiration. The internal respiration includes transport of gases, especially transport of oxygen and transport of carbon dioxide. You can see here, transport of oxygen and transport of carbon dioxide. So first of all, we will summarize the transport of oxygen because there are many details in this transport of oxygen. So transport of oxygen occurs by 2 ways. But prior going to these ways of transport of oxygen, you are familiar that human body contains blood contains plasma and RBCs. So this transport from lungs to tissue and back again will occur within these RBCs and plasma, or through these RBCs and plasma, right? And that's why in detail we will study the transport of oxygen through plasma and through RBC, right? So first of all, the transport of oxygen through plasma. Now you are well known that blood contains 90% water and 10% other constituents like RBCs, WBCs and platelets. The 90% water contains, or 90% of that fluid part of blood contains plasma. Basically, again in clarified condition, the exact percentage is 55% plasma and 45% blood cells. So that 55% plasma, which is a fluid part of our blood, transport only 3% oxygen. Only 3% oxygen. Or in another word, 3% of transport of oxygen occur through in dissolved state through the plasma. Clear? Now second way of transport of oxygen is as oxyhemoglobin, HbO. It is one of the complex molecule formed inside the RBC, right? So about 97%, you can see this percentage also, remember this percentage also because it will be asked in MCQ or for answering one sentence. So 90% oxygen is transported as oxyhemoglobin through RBC and 3% will transport through plasma. So overall roughly around 100% transport of oxygen, 3% through plasma and 97% through RBC as oxyhemoglobin, right? Now, what is this hemoglobin? Hemoglobin is one of the conjugated protein complex molecule. It is a respiratory carrier. It is a respiratory carrier. Remember, each and every point I have written on this board is very much important. So, hemoglobin is one of the conjugated complex protein molecule containing iron and heme. It is a respiratory carrier. It is a respiratory carrier, that means can carry oxygen. Secondly, it has high affinity for binding oxygen and form oxyhemoglobin. This hemoglobin molecule has high affinity. Affinity means what? Liking. The hemoglobin molecule likes to bind oxygen molecule. That's why it is termed as affinity. So high affinity for oxygen and form oxyhemoglobin. This can be represented with one reaction as such. Hb means hemoglobin can bind almost all 4 molecules of oxygen, or in another word, hemoglobin has 4 Fe, iron binding sites, to which this oxygen molecule can bind. So one molecule of Hb, so this is one molecule of Hb bind 4 molecules of oxygen and forms oxyhemoglobin. Or roughly, if you draw the diagram, suppose that this is hemoglobin. This hemoglobin has 4 such binding points. Each one can bind such one molecule of oxygen, total 4, forming HBO, 4. Right? So one molecule of hemoglobin can bind 4 molecules of oxygen and form Hb4O2, that is oxyhemoglobin, a complex molecule. And for your additional information, prior to binding oxygen, hemoglobin is colorless, or the RBC is colorless, because hemoglobin is present inside the RBC. But when it forms oxyhemoglobin, it gives bright color, and hence RBCs are red in color, and that's why the name is given red blood cells, yeah, or erythrocytes. Now, this oxyhemoglobin, when it binds at lung level, it is transported from lungs to tissue and dissociates at tissue level. So the binding occurs at lung level and dissociation occurs at tissue level, and it is transported through the circulation, through the blood, through the RBCs. When it reaches up to tissue, this complex molecule, bright red in color, oxyhemoglobin Hb4O2, dissociates again back into hemoglobin and 4 oxygen molecule. Right? And in that way, tissue gets oxygen. This binding of hemoglobin with oxygen depends upon oxygen tension. Now, in the last lecture, in the last video, we have studied the external respiration. And in that, we have studied that the partial pressure means what? The partial pressure means the part of pressure of single gas in a mixture of gas. A pressure created by a single gas into a mixture of gas, or inside the mixture of gas. That is known as partial pressure. Or in another word, you know very well, the whole atmospheric pressure, or in atmosphere, many number of gases are present, for example, oxygen, carbon dioxide, nitrogen, sulfur, etc., etc. So all of them, they exert certain pressure that is called as hole pressure. But inside that mixture of gases, only one gas exerts certain pressure, for example oxygen. Then that is called as the partial pressure of oxygen. For example CO2, the partial pressure of CO2, or in small or in abbreviation PPO2, PPCO2. Right? So we have studied already in previous video or lecture what is meant by partial pressure. Again, you are familiar that at lung level the partial pressure of oxygen is 104 mm of Hg, and in surrounding blood it is 40 mm of Hg, and that's why the always molecules or pressure moves from higher concentration to lower concentration, and in that way the oxygen rush inside the alveolar capillary network. Similarly, the partial pressure of CO2 is 45 mm of Hg in the alveolar capillaries, and inside the alveolus it is 40 mm of Hg. So ultimately, along concentration gradient, that means from higher concentration to lower concentration, from blood to alveolus, the carbon dioxide is released out. So that we have studied already in the last lecture. Taking into consideration that information, now this binding of hemoglobin with oxygen depends upon oxygen tension. That means PPO2, partial pressure of oxygen. How? Actually, 100% saturation of oxygen cannot take place. It is very much rare. It cannot take place. It is rare one. Only 95 to 97%. Only 95 to 97% saturation of at partial pressure 100 mm of Hg occur in alveoli. And just I have told you 104, maximum 104 mm of Hg is present in alveolar blood, and that's why at 100 mm of nearly about that 104, 100 mm of Hg, 95 to 97% of oxygen transport or saturation can occur. This saturation, that means now from alveolus, the alveolar capillary network containing blood, containing RBC, containing hemoglobin, they bind this hemoglobin in this way. This we have studied the reaction. They now start transporting or circulating from lung level to tissue level. When they reach up to tissue level, ultimately the PPO2 decreases. The partial pressure of oxygen decreases. So saturation decreases with drop of PPO2 and start dissociation of HbO2. That means oxyhemoglobin. Right? So as blood reaches near to tissue level, the partial pressure declines and decreases and decreases. The saturation also drops up, and now hemoglobin start dissociating oxygen molecule in this fashion. This we have studied in above reaction. The Hb4O2 dissociates back into hemoglobin and 4 oxygen. So at 30 mm of Hg of PPO2, only 50% saturation is maintained. 50% saturation is maintained up to 30 mm of Hg. This above relationship, that means the relationship of saturation of hemoglobin, saturation of oxygen, and the partial pressure is known as oxygen dissociation curve. So at 30 mm Hg, partial pressure, only 50% saturation is maintained. This above relationship between oxyhemoglobin saturation and oxygen tension is called as oxygen dissociation curve. So what is oxygen dissociation curve? In examination there may be a question. Define oxygen dissociation curve. So oxygen dissociation curve is the relationship between oxyhemoglobin saturation and oxygen tension. Right? So what is oxygen tension? Just we have studied above. Binding of hemoglobin with oxygen depends upon oxygen tension, that means partial pressure of oxygen. So oxygen tension means simply partial pressure of oxygen. Now we have drawn here this curve, oxyhemoglobin dissociation curve. In that we have plotted on x-axis partial pressure of oxygen in mm of Hg, and on y-axis the hemoglobin, that is oxygen saturation, percentage oxygen saturation. Hemoglobin percentage oxygen saturation. Remember both these actually phenomena. On x-axis what is, on y-axis what is. On x-axis there is oxygen or partial pressure of oxygen in mm of Hg, and on y-axis hemoglobin percent oxygen saturation. Right? How this curve is seen? This curve is sigmoid shaped normally. You can see here a sigmoid, normal sigmoid shaped oxyhemoglobin dissociation curve. Right? This sigmoid curve has certain features. The certain features are, this curve may shift to right. You can see in the figure. It is shifted to right. I have shown here with the help of an arrow. And I have drawn this sigmoid shape in dotted line towards right side as well as towards left side also. So it shifts to the right side due to, which are the causes of shifting of this oxyhemoglobin dissociation curve to right side? The causes are increase in H ions and partial pressure of CO2. Normally, this sigmoid curve shift to right side because of increase in H ions and partial pressure of CO2. Secondly, increase in body temperature. Body temperature is also responsible for shifting this sigmoid curve to right side. Thirdly, increase in DPG. Now what is DPG? The DPG is 2,3-diphosphoglycerate. This is one of the chemical component formed during glycolysis inside the RBC. The RBC manufactures its own ATP during glycolysis, and during that glycolysis process this DPG is formed, and when DPG increases, again this curve, sigmoid curve, shifts to right side. Right? This DPG formed inside the RBC declines affinity of hemoglobin for oxygen. That means when RBC containing this hemoglobin reaches to tissue level, at lung level it has greater affinity for binding because of oxygen tension. But when it goes and transported up to tissue level, the oxygen tension decreases. That means partial pressure decreases. Ultimately, the affinity due to DPG, the hemoglobin dissociates oxygen, and the oxygen is released in between interstitial cells of tissue and organ. Right? So these are the causes of sigmoid curve shifting to right side. Which are these causes? Again, we summarize. Due to increase in H ions and partial pressure of CO2, due to increase in body temperature, due to increase in DPG formed during glycolysis inside RBC, and DPG lowers affinity of hemoglobin for oxygen, and oxygen is released, dissociated from oxyhemoglobin into oxygen, and the oxygen will get or provided to the tissue. Now in our textbook, this shift is described as Bohr effect. Scientist Bohr and scientist Haldane described these effects. That's why on honor of the scientists, the names are given: Bohr effect and Haldane effect. Now what is Bohr effect? The Bohr effect means the shift of above curve, that means oxyhemoglobin dissociation curve, due to change in partial pressure of CO2 in blood. Right? And that's why it is known as Bohr effect. You can see here, high CO2, low CO2. Due to high CO2, it shifts to the right side. Due to low CO2, it shifts to the left side. Right? And normally it is sigmoid shape. When normal CO2 is there, ultimately the curve is sigmoid shape. But when CO2 increase, CO2 decrease, it shifts to right side and left side respectively. And accordingly, when low CO2 is there, ultimately high pH. When high CO2 is there is a low pH of blood. Right? So that is called as Bohr effect. Now what is meant by Haldane effect? In Haldane effect, the oxyhemoglobin functions as an acid. It functions as an acid, and this oxyhemoglobin decrease pH of blood. Just I have told you. The oxyhemoglobin decrease pH of blood, and due to increase in H ion concentration. Now remember, I have explaining here that oxyhemoglobin functions as acid, and here it lowers pH of blood. Lowers pH of blood means what? Tends to acidic condition. When acidic condition occur, when H ions are added to any solution, the pH of that solution goes to acidic condition. When OH ions are added to the solution, the pH of that solution tends to basic nature. Right? So here, decrease in pH of blood is due to increase in H ion concentration. Hemoglobin adds up H ions. That's why the pH decreases. pH decreases, that means pH tends to acidic condition. Right? And due to which, so due to increase in H ions, another way, the HCO3, carbonic acid formed in the plasma, changes to water and CO2. The carbon dioxide combines with water present in plasma, and a carbonic acid is formed. That carbonic acid is also formed inside the RBC also, to some extent. And due to increase in H ion concentration, HCO3 changes to water and CO2. This is known as Haldane effect. Clear? So now you are clarified what is meant by Bohr effect, what is meant by Haldane effect. In Bohr effect, the shift of oxyhemoglobin dissociation curve is due to change in PPCO2 in blood. Only one word is important: change in PPCO2, partial pressure of CO2. Haldane effect means change in pH, that means decrease of pH of blood due to increase in H ion concentration, and HCO3 changes to water and CO2. That is called as Haldane effect. And at last, now, due to all these study, or the summarization of all this study or oxyhemoglobin dissociation curve, in tissue, the partial pressure of oxygen is low and partial pressure of carbon dioxide is high. Right? And hence, now we'll start with alveoli at first. We'll go back. In alveoli, partial pressure of oxygen is high. Now you know very well how much? 104 or roughly around 100 mm of Hg. And ppCO2 is low. You know very well how much ppCO2? 40 mm of Hg. Oxygen bind hemoglobin. So at lung level, due to oxygen tension, a difference in the partial pressure of oxygen and that of CO2, the oxygen binds. In tissue, the partial pressure is low and partial pressure of oxygen is low and partial pressure of carbon dioxide is high. Then ultimately hemoglobin cannot bind oxygen. And at the tissue level, the dissociation starts up. The oxyhemoglobin dissociates into hemoglobin and oxygen. And the oxygen, thus release of oxygen for diffusion into tissue cells starts. And in that way, tissue cells gets the oxygen. Right? So here we complete the transport of oxygen under the internal respiration. One point is transport of oxygen. Okay? Now we'll summarize again. Under internal respiration, transport of oxygen and transport of CO2 will be studied. First, transport of oxygen, it will be studied by two ways again, through plasma and through RBC as oxyhemoglobin. Through plasma, 3% oxygen is transported. Through RBC as oxyhemoglobin, 97% oxygen is transported. Then what is hemoglobin? It is a respiratory carrier, have high affinity for oxygen to form hemoglobin. One molecule of hemoglobin can bind 4 oxygen molecules to form oxyhemoglobin Hb4O2. Oxyhemoglobin transported from lungs to tissue and dissociates again back into hemoglobin and 4O2. Binding of this hemoglobin with oxygen depends upon oxygen tension, that is partial pressure of oxygen. 100% saturation is rare, cannot occur, do not take place. Only 97%, 95 to 90% saturation of at partial pressure 100 mm of Hg occur in alveoli, and saturation decreases with drop of partial pressure and start dissociation of hemoglobin, oxyhemoglobin at 30 mm of Hg. Partial pressure only 50% saturation is maintained. This above relationship between hemoglobin, oxyhemoglobin and oxyhemoglobin saturation and oxygen tension is known as oxygen dissociation curve. This is plotted here in that manner. You can study. This curve has specific feature. It is sigmoid curve. It shifts to right side due to increase in HI concentration and ppCO2, increase in temperature, increase in DPG. What is DPG? The DPG is 2,3-diphosphoglycerate formed during the glycolysis in RBC, and DPG declines affinity of hemoglobin for oxygen. And by studying this, Bohr effect and Haldane effects are summarized. The Bohr effect means shift of above curve due to change in PpCO2. And Haldane effect means it acts as an acid, decrease pH, increase H ion concentration, HCO2 changes to water and carbon dioxide. And finally, in two lines only, in alveoli, PpO2 is high, PpCO2 is low, oxygen binds Hb. And finally, in tissue, PpO2 is low and PpCO2 is high. Hemoglobin cannot bind oxygen, and thus oxygen is released for diffusion into tissue and cells. So in that way, we complete this first part of internal respiration known as transport of oxygen. Now learn it at home. I will send the notes. Study hard. Go through each and every point by taking into consideration all these one. I will send the photo of this blackboard also, and learn this thoroughly. Remember this thoroughly. Otherwise, the next step, that is transport of carbon dioxide, is also complicated, much more than the transport of oxygen. So even only when you are understanding transport of oxygen, then only you will understand transport of CO2.